Hello everyone, we're Annalise Fetch and Mimiotra, and this is our presentation on Hydropower 101.
Hydropower is an energy resource that converts the movement of water into electrical energy, whether that be through a hydroelectric dam or a tidal turbine. One of the important aspects of hydropower is that it is a renewable energy resource. Renewable energy resources are constantly replenishing themselves and work to lower carbon dioxide emissions, one of the primary causes of global warming. For this project, the team decided to focus our efforts into learning more about the future of energy production and how hydropower plays a role. We formed a research question to help us hone in on our studies, which was, how does a hydroelectric power plant convert the mechanical energy of water into electrical energy?
There are two types of hydroelectric plants, hydroelectric dams and run-of-river dams. A dam is a river created to raise the level of water and control its flow. The elevation creates a gravitational force that produces a movement of the turbine. A run-of-river dam respects the river flow and redirects a portion of the river water through the turbine. How does the run-of-river dam work? The creation of energy that is made by hydropower plants consists in two essential parts: the process that the water executes in the run-of-river dam and the process of conversion that exists inside the generator. The run-of-the-river dam creates a drop from one water level to another. The water ends in a turbine that is moved by the current of water that is flowing through the dam. The shaft of the turbine goes into the generator, which produces the power. Then, the water stream reaches the generator, which is connected by cables to the power conductors outside the generator. Consequently, this process of water continues past the propeller and goes through the river. Here are some facts about the John Day Dam. The John Day Dam is one of the fifth largest hydropower plants in the U.S. This dam is near Oregon in the Columbia River. This river is an important step along the migration path of salmon. Also, this hydropower plant have 60 Kaplan adjustable turbines rotating at 90 revolutions per minute. As you can see in the picture, the river starts in the Pacific Ocean, then flows through the Columbia River where is located the John Day Dam. Consequently, the Columbia River joins the mouth of Snake River.
When determining how to model a hydroelectric dam, it became clear that there were two main components: a turbine that rotates in reaction to the flow of water, and a generator that converts the mechanical energy into electrical energy. We made the decision to model both of these aspects, relating the turbine to the general power output of the plant and the generator to the voltage produced by the plant. Finding the connection between these two also became a necessity. Voltage can be defined as the potential energy per unit of charge, being called EMF in the case of a generator. Power is the rate at which energy is converted from one form to another, in this case mechanical to electrical. The two are related by a simple equation. Multiplying the voltage by the current will give power in watts. A run-of-the-river hydropower plant has an equation used for power output. This equation is 1/2 times eta rho q v squared. Eta is the efficiency of the turbine, rho is the density of water, v is the flow velocity, and q is A times v, where A is the cross-sectional area of the penstock flow channel. Flow velocity changes second by second, so it is the quantity that will have the most effect on the power output. This meant that it was important to have quality data about the flow velocity of the Columbia River, the river the John Day Dam is located on. Luckily, the United States Geological Survey tracks the flow velocity of the river every day, 24/7. This is the graph for the flow velocity on May 1st, 2021, and is where we pulled our flow velocity data from. An important note is that we had to convert from feet per second to meters per second. The MATLAB simulation that was created can be seen here. This simulation implemented the power equation and the flow velocity data in order to make a prediction for a day's power output. This is only a sample of the code, as it was programmed to change for the flow velocity every hour. The pattern shown here continues until a whole day has elapsed. The simulation results can be seen in this graph. The primary part of interest is the slope, which can be seen to be changing throughout the curve. This is due to that changing flow velocity on the hour, changing the overall power output.
For this simulation, we built a circuit that primarily focused on demonstrating how a turbine spins in reaction to water passing over its plates. The water passing over the turbine's plates is a mechanism required to produce power. This then connects directly to the generator, which is shown in a separate simulation. The circuit itself was just a matter of having some weird hobby motor spin when attached to a power source. We also want to demonstrate how the hydropower plants can be adjustable to react to demand for power. This is the reason why we have the circuit program on our Arduino Uno, so we can have the hobby motors turned off at certain intervals. We have the motors attached to two different pins on the Arduino in order to allow each motor to be controlled separately. From the motor, they are wired back to ground to create a complete circuit. Generator operation. The generator is in charge of converting the movement of the water diving turbine into energy. When water enters to the turbine, it's passed inside the scroll case to the set of vanes called the wicket gates. These gates control the water that enters into the turbine. The wicket gates are controlled to open and close in response to conditions in a grid and overall demand of electricity. When the turbine is overloaded, the system of wicket gates slows down the turbine. When the system senses a demand of energy, it reacts by reopening the gates and returning to a normal water flow through the turbine. Continuing with this process, there is a tube that joins the turbine and the generator called the runner. At the top of the runner, the generator is attached. The generator has several layers that transforms water kinetic energy into electricity. At the top of the generator is the exciter, which is a DC motor power supply. In this part of the generator, wires are attached that pass the generated energy to an external controller called the automatic voltage regulator, or AVR. Inside the generator, there is a rotor that is attached to the runner. Inside the rotor, there is a stator. This part consists of a set of 3 coils of copper wire called windings. Also in here are a number of electromagnets that are powered by the DC current from the exciter and rotate together with another electromagnet that is in the rotor. These 2 electromagnets must always be aligned. This is the way in which the energy is created. The generator produces 3-phase power that distribute in different parts of the stator. This creates 3-phase alternative current.
Dynamo generators have a governing equation that dictates the EMF in volts. This equation is shown here, being 2 phi n rho z divided by 60C. C is either rho or 2 rho depending on the type of winding seen in the generator. For a hydropower plant, it is recommended to use lap winding, which correlates to the 2 rho value for C. Phi is the flux per pole leaving the generator, N is the speed of the generator in RPM, rho is the number of pairs of poles, and Z is the total number of armature conductors. To model the generator, we used a MATLAB simulation that implemented the dynamo generator EMF equation. The code can be seen here. The values of phi, rho, and z are constants, while n can change. However, we decided to hold the RPM constant to the maximum value seen at the John Day Dam, that being 90 RPM. The program will generate a plot that shows the voltage throughout the day. However, it is important to note that the simulation is only for one of the 16 generators at the dam. The result of the MATLAB simulation can be seen here. Again, the slope is of interest. It is observed to be linear, which is an important aspect of a hydroelectric dam. A hydroelectric dam will always have a constant maximum output voltage, met at the maximum revolutions per minute. The linear slope signifies a constant voltage output. We then decided to model the generator-to-grid connection in TinkerCAD. The circuit diagram is shown here. This simulation will be used to demonstrate how a generator in a hydroelectric dam will always send the same output voltage to the grid. An important component here is the voltage regulator, which is used to control the amount of voltage leaving the power plant to the grid to prevent damage to the grid. The part specifications for this circuit can be seen here, making changes to compensate for the lack of certain components in TinkerCAD. Primarily, we were missing a generator. A swap was made here, putting in a function generator which can be implemented to mimic a normal generator. Another part that was missing was the connection to the grid. This was where we connected a multimeter set to voltage. Here is a video of the TinkerCAD simulation working. It can be seen that the voltage increases as the capacitors charge. It then hits a maximum value under which the voltage will fluctuate as changes naturally occur within the capacitors.
In conclusion, hydropower plants can be very useful for supplying energy. The results agree reasonably well with calculations made beforehand, sustaining our resource question, since it was verified that the mechanical energy of the water changed to electrical energy during this process.
As a review of how this process works, a penstock guides the water into the hydropower plant, then water spins a turbine to convert the flow of water to mechanical energy. In turn, the turbine spins a dynamo generator to convert the mechanical energy into electrical energy. From there, a voltage regulator controls the voltage output flowing from the dam in order to not damage the connection to the grid. We hope you all have had an interesting look into hydropower and how it will play a vital role in our energy future. Thank you for watching our presentation.